Hello, I'm Renzo Huber. I'm an MRI physicist and postdoc in the MR Methods group, headed from Benedict Poser here in Maastricht in beautiful Netherlands. And I'm sitting here in front of the 70 console of the 70 scanner from Scanexus to go through a practical tutorial on the acquisition of layer-dependent fMRI. And this tutorial is in the context of the 2019 Minnesota workshop on ultra-high field MRI, particularly the educational course on laminar and layer fMRI organized from Cheryl Ullman. And I will try to do this tutorial as a hands-on tutorial with a lot of click-along sequences of the scanner console and a lot of practical examples. And I will particularly focus on layer fMRI with respect to issues and optimizations of high-resolution EPI, echoplanar imaging. You probably know that single-shot EPI is nothing else than just acquiring every point along this line of getting back and forth and back and forth and back and forth in this kind of two-dimensional case space. And there's really nothing more to it. It's as simple as that. And we will not talk about anything more complicated than this simple case of going back and forth and back and forth and back and forth. And even though you can easily describe this simple geometric pattern here to anybody, like even a 6-year-old, there are quite a few parameters necessary to really fully parameterize this simple going back and forth when using it in an fMRI time series. So at the scanner, you usually have parameter task cards like this here, where you have multiple parameters and also multiple task cards, and some of them even have sub-task cards, and there are a lot of parameters stored on there. And most of these parameters are kind of interrelated and kind of connected and complicated in a very nonlinear fashion. And that's really a problem in layer-dependent fMRI. And the problem, in fact, is that these parameters are just the tip of the icebergs. There are many, many more parameters hidden in the system that are quite important for us too. And in this tutorial, I want to focus on those hidden parameters. And those hidden parameters, they're not really so important for conventional fMRI. That's why they didn't really get their own parameter in the protocol editor, but they're still important for layer-dependent fMRI. So I want to show you how to change them and how they affect the signal at the end. And I want to do so with this hands-on tutorial by doing one scan session together with you, going through every setup step that I usually do when I acquire layer-dependent fMRI data. So also note that this is kind of my personal way of doing things, so see this as an educational exercise. And I'm not really claiming generalizability on a scientific level here. If you want to look at the raw and process data, you can download them here from OpenNeuro. You can also download the scan protocols that I use in this scan session that we're going to go through now. And the sequence that I will focus on, as per request from Cheryl, is a very standard EPI, which acquires an entire case-based plane within one shot. And I will mostly focus on Siemens 7 Tesla systems, which is kind of the vast majority of layer-dependent fMRI scanners worldwide. However, I believe that almost every parameter that I will talk about here has some pendant for Philips or GE scanners or systems too. So the scan session that I will go through now is conducted on a Magneton 70 running on VB17, and it's a 70 scanner of the Scanexus company that is based here in Maastricht. However, I will also talk about some additional data from time to time that are acquired at NIH in the section of functional imaging methods, or fMRI-F, at NIH in Bethesda in USA. If you want to download these slides also to go through them in slower time, you can download them here. So let's start and go through every click together. So Artie, our participant, is in the scanner already, and as soon as the participant is registered and the standard localizer is executed, your console might look something like this. And there you already see one of the first challenges of layer fMRI. While the localizer is really optimized to be super fast, like a few seconds only, and it gives you kind of the rough geometry of the brain. You know how big it is, you know where it's positioned, and it really helps you to adjust your whole brain protocol accordingly. It is not really helpful for layer-dependent FMRI, because in layer-dependent FMRI we are often limited with a smaller field of view protocol that needs to be aligned to a very specific sulcus in your brain. And you can see here that the sulcus structure is not really visible. And we only have a few slices only, so it's very hard, for example, to adjust the slices to an area that is not by coincidence covered with these 3 projections. So what I use instead is a 2D inversion recovery turboflash. This is a product sequence that's on any scanner, and if you want to set up 2, you can easily take this protocol and set it up on your machine too. And what this does is it acquires multiple slices in each direction, and it also uses an inversion pulse, meaning that you have a much better gray matter, white matter contrast. But because there are many more slices, it also takes a bit longer. It takes up to a minute or so. This is not really a limit with respect to timing, however, because it's a 2D protocol, so you can just drag and drop the images as they come in, and even after 5 seconds, you already can start to align your slices. If you wait the entire minute, then all the slices are completely collected, and here you can also clearly see how well the sulcus structure is visible in this protocol. For example, in this case of this protocol here, I would like to simulate how we would do a layer-dependent fMRI acquisition for a visual protocol. So there we would, for example, care about this calcarine sulcus, which is easily visible here. And as usual, in layer-dependent fMRI, our field of view is limited. So here I'm simulating a case of 26 slices with a sub-millimeter resolution, kind of aligned the calcarine sulcus here. So the imaging volume would be the one in yellow over here. The shim volume for the B0 shim is indicated in green. And you can see that because we have a small field of view for our imaging, it's also advantageous to only shim a smaller volume, and the green box is not covering the entire brain. However, I don't make this green box too small, especially not as small as your conventional field of view for imaging. And this has multiple reasons. And one of the reasons is that the field map that Siemens, in this case, uses to do the shimming and optimize the B1 plus and homogenize it is not that high resolution. Usually it has resolutions of like 3 to more often 6 millimeters. And this means that for a small shim box, like that is as small as the imaging volume, you would only have like 2-3 voxels of your field distribution within your field of view. And it's obviously impossible to fit higher order spherical harmonics of your shimming to these like 3 voxels, right? That's why it's more beneficial to use larger shim boxes over here as indicated in green. I also always make this shim box a bit larger to cover the entire slice. So even though we only care about the field of view down there, the calcarine sulcus and the visual cortex, I still contain all the entire slices and even the frontal part into the shim box. And this is due to the fact that at these very high resolutions that we want to use, the bandwidth is usually very low. And the Nyquist course correction in EPI is done in Casebase. This means that every voxel here contributes to the Nyquist course correction. So sometimes when the shimming is very bad in front here, it introduces artifacts that are distributed across the entire image and therefore also corrupting your ROI back there, even though the ROI back there was originally not as compromised with respect to inhomogeneities. Maybe also important to note here is that for most of the shim algorithms out there, the shim is binary, which is also kind of unfortunate and not really what we want in layer-dependent fMRI, but it's how it is. And with binary, I mean that your voxel is either inside this green box or outside that green box. So it either contributes to your shim optimization or it doesn't. And this is the case even though we actually have a kind of more continuous interest. We want to have, for example, the highest shim accuracy back there, where we only want to tolerate off resonances in the range of like 10 to 20 hertz. Whereas within the entire EPI, here, for example, we could deal with higher off resonances, for example, in the range of 30 to 40 Hertz. And outside, for more advanced protocols, for example, in VESO, we would be able to tolerate off resonances in the range of maybe 50 Hertz or 100 Hertz, depending on the bandwidth of your inversion pulse. However, we cannot really adjust that. These different kind of optimizations locally, it's binary. It's either inside or outside the shim box. So as soon as the shim is done and all the parameters in the sequence task card are set up, we can access these hidden parameters that I talked about earlier that did not really get their own field in the protocol editors visible here. And you can access them with an editing tool that is called Expeller. And you can access this Expeller by clicking Escape and Control and Escape at the same time, which on VB17 system would give you a window like this one, and you have this run option here. Then in this run option, when you click it, you get this field that you can use to type in certain commands and start, for example, Expeller tool. So just type in Expeller here, and then you will get this editor. And if you click this button, the open document button, you will get an additional window, a menu where you can select the file that you want to open. And the interesting file that we care about is the ICE config. And it's particularly at this path. So the path is written out here again. It's on C, medcom, config, ICE config EVP. So select that one. Usually it's the one that's already kind of pre-selected. If you are on a VE system, for example, on the new Terra platforms, this menu might look slightly different. So if you hit the Control Escape combination on your keyboard, you might get a window like that where you can start this command prompt, for example, or like just basically a console. As soon as you do that, then you get your command prompt or your console, your terminal, and there you type in the commands for your tools just like that. You don't have the run window anymore, but you can just type in Expeller and you will get the same kind of tool to edit all these other parameters. So this is the file now, this ICE config EVP opened in the Expeller tool. And you can see that there are a lot of different parameters listed here. And a lot of them are actually quite important, specifically for layer-dependent FMRI, and maybe the most important ones are hidden under the family of IcePad. So if you click on that, you see all the parameters that you can change here. And the first parameter that I always change as soon as I do a layer-dependent FMRI study is switch on the improved cropper. So here under ICE config iPad, you have a parameter that's called improved cropper, and for each parameter that you have in the Expeller here, you usually have a value up there, and if you're lucky, then the guys from Siemens also wrote a quick short comment about it. And here for the improved cropper, you see that is a global flag to use a slightly different cropper algorithm. And on default, it's switched off. If you want to switch it on, you need to change the -1 to a +1, like that. As soon as you did that, you can save it. And now, for all the runs in this session, you will use the improved cropper. And maybe it's important to note that not only the open protocol will be affected by that, but every protocol within your session will use now this algorithm. As soon as you put a participant out and register a new subject, then everything is overwritten again, which is, I think, a nice feature because it means that you cannot really screw it up for other people. Whatever you change here will be overwritten as soon as a new participant is registered. However, it also means that every time you register a new participant, you need to change these parameters manually over and over again. And it's kind of annoying, but if you know where to click, it usually does not take much more than 30 seconds. And you can actually also do this before RT is on the table. So one thing that I always change is the improved cropper, or as already said, and it's kind of weird why it's not on by default on its own. Even like Siemens is confident enough to call it improved cropper, so why not use it? And here on this slide, you can see the effect that changing this improved grappa parameter has on actual data. So here I'm flipping back and forth between the default, the improved grappa, the default, the improved grappa, back and forth. And you can see that it changes the weighting a bit, which doesn't really affect our fMRI signal a lot. As long as this weighting is constant, we usually only care about the temporal fluctuations. You might be able, if you want to see it really, that in the white matter we have more of the speckle noise for the default compared to the improved grappa. However, this TSNR improvement is really, really tiny. So when you look at the TSNR, then you might be able to see a slight improvement. Usually it's only in the range of like the single-digit percent changes. So here it's maybe 1 or 2%. You might be able to see that the ghosting is slightly improved for the improved grappa compared to the default case. Here you see the same thing from another data set collected at NIH. Here the TSNR was lower to begin with, and flipping back and forth between the default and improved, you can see there's a slight like maybe shift of TSNR values like locally, but the effect is rather small. You might be able to see that right here there's a bit of like ghosting reduction, which might help a tiny little bit. The reason why I changed the parameter to this improved grappa value, however, is because doing so allows us to change a lot of other parameters on top of that. So as soon as we change this improved grappa parameter, it also allows us to change a lot of other things in the grappa algorithm. For example, here 2 values down, you see this grappa noise reduction 1 parameter. And this is a field that denotes and sets the strength of your regularization during the grappa kernel fit. So when you do grappa, you usually leave out several case-based lines. In this example here, in this toy example, it's every other case-based line is not acquired, and based on reference data, you can try to recover the signal from this data based on the signal from a neighboring case-based points. And this means that you have reference data, and the weighting between these neighboring case-based points and the missing data point here needs to be fitted and determined from this reference data set. And the regularization strength of this grappa kernel fit is set by this parameter. And this parameter, as I said, is only used when the improved grappa is switched on. If you want to learn more about the concept, how this works, you can check out this blog post over here. Usually, when I change this parameter in layer-dependent fMRI, I change it from 1 to something in the range of like 3000. And this has a much stronger effect on the data at the end. So here, for example, this is the layer-dependent fMRI signal for default of the regularization strength, and going to like 3000, you can see that a lot of this speckle noise and salt and pepper noise is really reduced, which is also even more so if you go even further to values not to 3000 but to 40,000, where you see that a lot of this noise is reduced, however, and the artifact level is significantly increased. So you don't want to overdo this regularization, because then that the artifacts become worse. And the same is visible when you look at the TSNR here, where you see that like the dark TSNR values in the like single-digit regime in the white matter are significantly increased for using the higher regularization strength. The same is true also for gray matter. If you overdo it and go to too high values like 40,000, then the TSNR might be high, but the signal also is not really local anymore, and then you have a lot of ghosting. And here is the same thing for an alternative data set from NIH, where you see the same thing, that increasing the regularization really improves your TSNR. And I think there is no reason why we shouldn't play with this parameter. There is no reason why all the universe of MRI and acceleration should use the same exact grappa algorithm, because if you do like liver imaging at 1.5 Tesla or layer-dependent fMRI at 7 Tesla, obviously you have a very different coil setup, a very different sensitivity to ghosting or B0 homogeneity. So it makes sense for every setup to also optimize this parameter too, as you would with any other parameter like echo time or TR or so. And in my experience, this parameter has a much bigger effect the lower your data quality is at the beginning. So if you have very low TSNR and kind of shitty data quality to begin with, increasing the regularization strength really helps a lot. And here in this case, it multiplies your TSNR, almost doubles it. However, when you have very good data to begin with and very stable signal already, more than in the double-digit regime of TSNR values, then increasing the regularization strength doesn't really help so much. Usually in layer-dependent fMRI setups that I've been working with, changing the regularization strength to a value of 1000 to 3000 usually doesn't increase the ghosting too much, and you are on the safe side. Oh, and of course, this is like my personal choice, and having these kind of increased ghosting, of course, means that you need to make extra efforts in your analysis to make sure that this ghosting doesn't really affect your analysis altogether. The next thing that you might want to think about changing is the parameter of the Krapper kernel size, which is just a few parameters below the regularization strength. And the parameter determines how many data points in the proximity of a missing data point are used to recover the signal over there. So in the example from earlier, where we omit every other Casebase line, we use the neighboring ones, the solid circles here, to recover the missing signal that we did not acquire right over there. And in this example, we have a matrix size of 3 by 2. So we have 6 data points altogether to recover the missing data point right over here. This means that our Krapper kernel size would be 2 in the phase encoding direction and 3 in the read direction. And the default here for the phase encoding direction is 4. So the Krapper P size, the P stands for the phase encoding direction. And sometimes, depending on your experimental setup, you might want to consider changing this from 4 to 2. Similar also for the Krapper kernel size in the read direction, which has this weird confusing name of Krapper segments, and the default is 3, and you might want to consider changing this to 5 depending on your experimental setup. And I found it helpful to adjust this parameter while keeping in mind the fundamental concept of Casebase, namely that a small object in Casebase, like a small kernel, refers to a smooth object in image space, whereas a large object in Casebase refers to a crisp image in image space. So for example, if you have very few, very big receive coil elements only, for example, like 16, 24 channel coil, or even for the 32 channel Nova coil, very often if you have a small field of view, the coil sensitivity in your image is rather smooth. This means that a small Krapper kernel can easily capture the local distribution of the individual coil sensitivities, and you might be better off using a small kernel. However, when you have very large field of views, or in cases where you have very, very small RF coils, for example, microstrips or something, then the coil sensitivity might be containing a lot of higher local spatial frequencies, so there you might be better off with a larger kernel. And obviously you also want to consider your specific ROI that you care about, because that's also affected by the choice of the size of the Krapper kernel. So in this example here, I show you simulation results of a small kernel. For a small image in Casebase, we have very smooth G-factor penalty maps. And the largest G-factor, that's usually somewhere in the center here, is kind of smoothed out. When you use a larger kernel, then the object in image space is more crisp and sharp. And therefore, you see that the G-factor penalty is very, very high and very locally confined here. So with respect to the ROI, I want to say that if you really care about this area right in the center here, for example, if you want to do a motor mapping of activity of the legs or something like that, and you really care about this region, you might be better off using a small kernel size, because then a lot of this higher TSNR kind of leaks into the center of the brain. Whereas when you care more about activity of like finger tapping, which would be somewhere there, you might be better off with a sharp G-factor penalty map and using a larger kernel that keeps all the noise in this location and does not really leak it to that location over here. If you want to read more about the background, you can check out this blog post over here. And the effect on the Krapper kernel size on our participant RT in the scanner right now can be seen over here. So going back and forth between a small kernel, large kernel, you can see that the signal intensity is almost not affected. It's better visible maybe when you zoom in. You can see that maybe in the center of the brain there are slightly different shadows on it. But then the real effect can only be seen if you look at the TSNR, for example, particularly in this data set where I used the same data and just reconstructed them with two different kernel sizes. So this is a small kernel, this is a large kernel, small kernel, large kernel, small kernel. And you can see that it's not that hugely different. However, it has a tiny bit effect, for example, in the center of the brain. So for the larger kernel, the TSNR is lower in the center and more locally confined, whereas for a smaller kernel, it's more distributed. And this might be even better visible when you just look at the TSNR improvements going from a smaller kernel to a larger kernel, where you see that for the larger kernel, we have a TSNR reduction, usually in the range of maybe 5% TSNR reduction in the center, where the G-factor penalty is the highest. However, you have an improvement in the periphery around that center, because there the G-factor penalty becomes sharper. The data that I usually change when I do layer-dependent fMRI refers to the partial Fourier imaging. So in layer-dependent fMRI, we usually have very big matrix sizes, and therefore we can only achieve reasonable echo times if we do partial Fourier imaging, even though everybody knows that partial Fourier imaging results in some sort of spatial blurring. We sometimes just don't get around using it at all. But if you use it, then I try to usually at least use an appropriate reconstruction algorithm. And there are different predefined algorithms for Siemens that we can choose from. For example, there is Magrosian, zero filling, submatrix, or POX. And I think zero filling is the default, whereas POX is the algorithm that's usually more effective in recovering high spatial frequencies, which usually results in lower TSNR values, but at least we are closer to the nominal effective resolution. However, the default parameter when using this POX is that it only uses 2 iterations. And this means that the reconstruction is maybe a few hundred milliseconds faster as opposed to, for example, more iterations. However, sometimes it doesn't really converge to a good value yet. So I usually change this parameter from 2 to 8. And the effect on those data can be particularly well seen in this phantom here that has a lot of bubbles in there. And also this means that there are a lot of B0 inhomogeneities that partial Fourier sometimes cannot really recover and has problems with. So with zero filling, it's not really sensitive to these inhomogeneities. You don't have these ring artifacts that you have in other algorithms. However, there's a lot of smoothing in the phase encoding direction. While Magrosian recovers most of the spatial resolution, it has these huge sensitivities to B0, and sometimes the signal is completely gone here. POX is some kind of a compromise between those, where you have some sensitivity to these B0 effects and you recover some of the spatial resolution, but it's kind of the best trade-off, I think. And in layer-dependent fMRI, you sometimes see that with a POX of 8 iterations, you will, if you want to see better, see these laminar features here, for example, indications of the layer 4 in the sensory cortex. Another thing that we usually need to optimize when we acquire layer-dependent fMRI data refers to the speed of going back and forth in this EPI train that we already talked about. And usually each line here in going through this Casebase refers to a very specific gradient pulse. And this gradient pulse can look something like this trapezoidal shape, where you switch on the gradient, you keep it on for a while, and then you switch it back off. And usually we want to go through this Casebase in layer-dependent fMRI as fast as possible, within certain external limits. And some of the external limits, for example, are the gradient power, how the gradient is built, how fast it allows you to switch it on and off, and how strong it can be, also in connection with the power of the gradient amplifiers. Another external limit of how fast we can go through Casebase refers to the peripheral nerve stimulation limit. So if you switch your gradients on and off again very, very fast, this can induce electrical currents in the body of your participants, which are not really comfortable. So there are peripheral nerve stimulation limits. And for most of the 7 Tesla scanners out there, they are equipped with these very large body gradients, meaning that the peripheral nerve stimulation limit is actually a larger limit than the actual performance of the gradient and the gradient amplifiers. So I am usually much more limited by that than the actual power. Another external limit that needs to be considered when we want to go through Casebase very, very fast are these acoustic resonances. So by going through Casebase, switching it back off and on and off and on again at a certain frequency means that you put a lot of energy into the system and it can kind of start to vibrate. So a lot of energy that you put into the gradients at certain frequency kind of builds up, it shakes more and more and more and more, becomes very, very loud, and the eddy currents are pretty bad, which are a huge challenge for the low bandwidth that we usually have in layer-dependent fMRI. So within all those limits, we want to optimize the gradient pulse shape here to go through Casebase as fast as possible. And you can see that this gradient pulse shape needs about a handful of parameters to be really fully defined. And important parameters, for example, are the rise time, so the speed on how fast we can switch on the gradient, how strong the gradient is, the magnitude here, and also the duration of this flat top. And also important sometimes can be the ratio of the ramping time versus the flat top, this plateau over here, especially the ratio of how long we acquire data while the gradient is still being switched on versus the time we acquire data while we have this plateau over here. The entire shape of this gradient usually can be summarized as the echo spacing in milliseconds. And even though we have these kind of handful parameters here, Siemens sequences usually do not really allow us to optimize all of them independently. In fact, most of the sequences only have one single parameter to optimize all those 5 free degrees of freedom. And this is the bandwidth. And the bandwidth field in most of the Siemens sequences does not really refer to the bandwidth alone, but as soon as you change the bandwidth field, it actually also changes the magnitude of the gradients, it changes the amount of ramp sampling, and obviously the bandwidth itself, meaning the duration of how long you are actually acquiring data, how long the listener is listening. And it's adjusting them in a very nonlinear fashion. So when you increase the bandwidth, going from very low bandwidth faster and faster and faster, it increases both. It increases the amount of ramp sampling and the magnitude of the gradient. As soon as you reach the maximum amplitude that the system allows you to use, which is, by the way, not really the amount the gradient could actually give you, but it's kind of an internal limit for your EPI. As soon as you reach this maximum amplitude, then the amplitude does not increase any further, and by increasing the bandwidth even further, just changes the amount of ramp sampling and reduces it respectively, while still also reducing the timing of listening and acquiring data. Some sequences have this additional parameter of free echo spacing, which kind of paradoxically does fix the echo spacing, but it allows you to manipulate the bandwidth for a given echo spacing, meaning that the duration of this gradient shape is not changed anymore, but by clicking this parameter you can change the amount of ramp sampling and magnitude. But both of those parameters are actually not touching the slope at all. So it's always the slope of this gradient is always the same. There's one other parameter that slightly allow us to manipulate the slope, not very continuously, but in a kind of binary fashion. So, or sometimes there are 3 options allowed, namely normal, fast, or fast plus or something. And as soon as you select a different gradient mode here, you switch to another slew rate. So here, for example, going from fast to normal gives us very similar behavior of bandwidth, just with a slower slew rate. Different than the common misconception, the echo time, however, does not affect the timing of this echo train at all. In fact, the echo time field in the protocol editor only manages possible delay time after your excitation pulse before the sequence starts to go through Casebase at all. It does not change anything of the gradient shapes over here. Here you can see how the speed of our going back and forth pattern and the gradient waveforms affect the EPI signal. And I would like to point your attention specifically to the second row here, which would refer to the TSNR of an example dataset that's also uploaded to OpenEuro that you can browse for different bandwidths. So here I start with a low bandwidth and I just increase it further and further and further and further. And you can see that the echo spacing is affected by that, obviously, in a nonlinear fashion. So, for example, here for 1500 hertz per pixel, the echo spacing is the shortest. If we increase the bandwidth even further, then we have, again, a longer echo spacing. So we just reduce the amount of time the ADCs are on and the data are acquired, but the timing of the EPI echo train is actually being slower again. And you can see that roughly speaking the TSNR is highest for lower bandwidth and then being reduced as you go to higher and higher bandwidth as expected. But also note the ghosting in the background. You can see that the higher bandwidth we use, especially as beyond this minimum echo spacing here, the ghosting increases more and more and more, and it can be quite huge. So here for the very high bandwidth, the data are actually not usable, and this is partly due to the fact that we are very, very close to the acoustic resonances. However, you see that here the echo spacing is very similar for this case and for that case. So also the acoustic resonances are very, very similar for those two cases. However, the amount of ramp sampling is different for those cases, and therefore it can be beneficial to use lower bandwidth than using higher bandwidth. So the take-home message here is that for any protocol that you set up, there's always a sweet spot in your bandwidth, and it's really worth it to try a few bandwidth and see which gives you the best SNR while still keeping the ghosting at a minimum level. While it is important to mind the switching rates of conventional like EPI trajectories in the layer fMRI time series, it's even more important to consider the imperfections in the readout and the corresponding phase inconsistencies in the acquisition of the Krapper reference schemes. And it is so important that people usually don't really worry about like efficiency or speed requirements just to get good Krapper acquisition like reference data. So in Krapper, as you know, certain case-based lines are usually omitted, indicated here in the kind of dashed case-based lines. For the training data and the Krapper reference data, however, we need to acquire all the different case-based lines to train the Krapper kernels in the first place. And there are usually different ways implemented in the sequence that allow you to acquire also these missing case-based lines. And one approach would be a so-called single-shot approach, where you acquire all the case-based lines, the ones that are later omitted and the ones that are not omitted, in a conventional EPI fashion, where you acquire them going back and forth and back and forth and back and forth. This approach, however, is not really applicable for layer-dependent fMRI, simply because for layer-dependent fMRI, our matrices are usually very, very big, so our case space is very, very big. And this means that the readout of the single-shot approach would be very long. It's already too long if we omit the case-based lines, but without omitting them, you can easily get into the regime of 150 to 200 millisecond readouts, which is really not sensible, considering that the T2 star is in the range of 25 milliseconds, so most of the signal would be decayed before you even go to the case-based center. Other approaches to acquire your case-based reference data are, for example, segmentation or fleet approaches, where you use multiple shots. In the first shot, for example, you acquire every other case-based line, and then after those are acquired, you shoot again, do another RF pulse, and acquire all the missing case-based lines, and together then you have a complete case space. And the difference between the so-called segmented approach or fleet approach is that in the segmented approach, you acquire those two different shots across adjacent TRs, whereas in the fleet approach, you acquire them right back to back. Even if you have a multi-slice approach, they are acquired right consecutively. Another approach, however, is to not use EPI-based reference acquisition schemes altogether, but use it in a flash-based acquisition scheme where every individual case-based line is its individual shot, and it can take quite a while until you acquire it. But since you shoot individually for every individual case-based lines, you don't really have so much problems as you would have had for the single shot. And since all these advancements of the grappa reference data acquisition schemes are rather recent, it's not really standardized just yet how this is implemented in the sequence. And you might be familiar with acquisition schemes or that look like that here in your protocol editor. The top ones, for example, for VB17, the bottom ones for VE11. So they are slightly different. Some options are missing in some sequences and sometimes not, but usually they refer to some section and collections of these different grappa reference acquisition schemes. And here you can see how this affects the data quality of our participant RT. So, and most of the data that we looked at so far used a flash acquisition scheme, but we can also look at, for example, the fleet acquisition scheme here, and going back and forth, you might not really be able to see a lot of difference. In fact, there isn't a lot of difference here. If we go to the segmented acquisition scheme, however, you can really see that it is quite different in multiple aspects, not only with respect to the noise level that's reduced, the noise level is actually increased and the signal to noise ratio is reduced going to segmented. And on top of that, it's also the ghosting level that's increased. And unfortunately, this segmented EPI approach has been the default setting for many systems and sequences until now. You can see it maybe more clearly comparing the different approaches here in the TSNR maps on the right, where you see that the segmented approach is really the worst case of doing things. The TSNR is the lowest, whereas for fleet or flash, the TSNR is increased significantly. And in my hands, personally, usually I see that flash slightly outperforms even fleet by a few percent points. Another parameter that is very helpful to play around with, especially during the period of setting up a new protocol, is the phase. For example, because the phase really tells us very clearly anything about what's going wrong with B0 related artifacts, for example, inhomogeneities. And this parameter is so important that you usually don't really need to go to the hidden parameters. Many sequences actually allow you to change this parameter directly in the protocol editor. In this sequence here, for example, from VB17, from a classic 70, in the contrast task card, in the dynamic sub-task card under the contrast task card, you have this reconstruction field allowing you to choose if you want to have the magnitude of the time series or both the magnitude and the phase. In another sequence here, for example, from the Terra on VE11, you even have like more fields that you can change. For example, you can say I want to have the magnitude only or the phase only or both magnitude and phase. And what you usually then get here in our example from our participant RT is two time series, a magnitude time series, and a phase time series. And the phase sometimes gives you good indications of the inhomogeneities here. So for example, you see that the shimming that we did at the beginning of the session did a fairly good job, I think. Most of the brain, especially the middle part and the frontal part, are quite homogeneous. There are not a lot of phase wraps. This was only possible for the shim algorithm, however, by kind of sacrificing the homogeneity in the back of the brain. So you see a lot of phase wraps back there. And this can sometimes be a problem. You don't really clearly see this in the individual images of the magnitude time series, but especially as soon as you run offline TSNR, then you can see like inhomogeneity problems there, especially like phase inconsistencies that change with very small field drifts. There are a few things that you can do about it as soon as you detect those. For example, One very effective way that is super easy is just switching the face encoding direction. Sometimes then related artifacts are just moving somewhere else. The inhomogeneity, of course, is still the same, but the artifacts are kind of manifested in a different way. Another very effective way is to manipulate the shim currents manually. So if you really don't care about the frontal part of the brain and you care much more about the back of the brain, you can try to make the back of the brain more homogeneous by only like slightly manipulating and sacrificing the homogeneity in the front. For example, here you could achieve more homogeneity back there by, for example, increasing the A22 shim current. Or in first order, it might also be considered as a linear bias here, so you could actually just reduce the B11 shim current. And if you do that in an extreme case here for the top two images, you see for a new time series where I manipulated this B11 shim current, I get this magnitude time series and this phase. And you can see that the phase now is much more homogeneous back there. There's almost no phase wrap in the back. However, the front is now completely screwed up. And it depends what you want to image with the highest quality at the end. Usually a compromise would be the best. And these kind of inhomogeneities are then clearly visible here also in the magnitude data. So for example, you have these kind of darker spots, and in my understanding, they are usually weird interaction of the Krapper overregularization on top of these B0 related artifacts. So they are sometimes hard to spot, and as soon as you fix one, the Krapper or the B0, then those artifacts go away or at least move a lot. Usually, in my experience, I always have some spots in the brain where I have these dark spots. Sometimes they come along also with increased ghosting, then you definitely need to do something about it. Sometimes the ghosting is not too bad, but you still have these black spots. So in the case down there, I, for example, did not manipulate the B11, but the A11 shim current. And then you see that the frontal part is now kind of resolved. I don't have these black spots anymore, but I have a new spot right over there. And you can try to move them around by manipulating the shim currents, dependent on the local pattern of the phase wraps. Or sometimes it also just helps to flip the phase encoding direction. Then the phase errors accumulate in a different way, and these black spots are usually not completely gone, but at least moving to another direction or another area of the brain. So playing around with those sometimes really helps, especially if you can sacrifice some parts of the brain in order to get one area here, for example, the dorsolateral prefrontal cortex with the highest maximum TSNR that you wish for. So now I would like to go through a different procedure of manipulating reconstruction parameters. Namely, in Siemens, there is a way how you can change the reconstruction post-hoc, like retrospectively, after the data have been acquired already. And this can be very helpful for multiple things. For example, in case you made an error and want to fix the reconstruction after you acquired the data already. Or it can also be helpful to take the same original data and reconstruct them in different ways by changing one parameter, for example. So you would have a very direct and honest comparison of the effect of this parameter by using the same input data and just changing the reconstruction pipeline. And this can be done by, again, hitting the Control Escape key on the Siemens keyboard simultaneously, which gives you this Windows XP menu here. And again, hitting the Run button. And now not typing in Expeller, but Twix. And on VE, this might again look slightly different. For example, you might not have this Run window, but use the command prompt. And then just type in Twix, which will give you a window that might look something like this. And this is basically a list of all the raw data that have been acquired in the recent time. Here, for example, we have a lot of raw data. We have a lot of time series. Those are usually the bigger ones. Here, I think 100 time points are in the range of 10 gigabytes. And in between, we have the phase, like the frequency adjustments. And you have this kind of duplicated left and right, whereas on the right side, you have clear timestamps when it was acquired. On the left side, you have kind of the entire family of parameters. I would advise you to always, if you change something, select it on the left side. Otherwise, the reconstruction later might choose the wrong one. For VE, this is fixed, that as soon as you click it on the right side, it also selects it on the left side. Now let's change a parameter in this time series, for example. If you want to change something, you can click on this button over here, which will give you the additional edit menu over here. And as soon as the right or any time series is selected, you will get something in the field down there. And this is now a temp file that contains all the important parameters for this time series. And you can open it by clicking this edit button here. And now this automatically calls Expeller, the editor. But now we are not looking at the config EVP. Now we are looking at all the reconstruction parameter of this specific sequence. So everything that was in the EVP earlier is also included here, but here we have many more additional parameters. For example, there are reconstruction parameters that are very specific to a given sequence. For example, in EPI, a parameter like this one here that is called eye online phase correction. This refers to a Nyquist course correction EPI that we will manipulate in the next step. And this is a parameter that only applies to EPI. Therefore, it is not included in the EVP ICE config file, but it is definitely included here. And here the default parameter would be 68. So for now, let's not change it, but just reconstruct it again. So we can hit the save button and then click the start over here. As soon as you do that, then it will load all the data. While the data are loading, you will get this green arrow. And as soon as all the data are loading, but the reconstruction is still running, you get a symbol like this laundry bucket over here. And when the entire reconstruction went through, then you usually get this kind of check. Now we reconstructed the same data set again, actually in this case without changing anything. And this means that we have a new time series now saved in our Pixel database, and this is automatically loaded to the patient browser. So on your Siemens keyboard, when you click this button or navigate to the patient browser by other means, then you will have an additional time series. So we earlier chose that time series and now reconstructed it. And so we have an additional time series right now. And it has the same description, everything's the same, but you have this additional RR description in the naming of the file. And this RR stands for retrospective reconstruction. And now let's manipulate this phase correction algorithm that I just talked about earlier. And you know that in EPI, we go back and forth in Casebase, and usually gradients are not perfect, so we have kind of delays between odd and even lines. And this is the same for any EPI on any vendor, and the different vendors have different ways on how to deal with those. But most of the time you have some kind of shifting or alignment of odd and even lines. So for example, here we focus mostly on the RI of the visual cortex. And when we look at case-based lines, we go back and forth. You can see that the case-based center, where all the signal is aligned, is kind of slightly shifted for odd and even lines with a certain time delay. And the time delay in the acquisition can be corrected for with a phase correction in Casebase. And this is known from any EPI textbooks and also extensively being explained on the educational sessions of ISMM, for example. And usually people just talk about the kind of zeroth order correction where you just align them with respect to each other. In layer-dependent fMRI, however, we have much bigger problems. We need higher order corrections too, because in layer-dependent fMRI we have particularly low bandwidth, and it takes quite a while to go through Casebase for layer-dependent fMRI because it's so big. And this can be a problem, for example, when the ROI, the region of interest back here, has a slightly different eddy current compared to RONI, a region of no interest. And we know that the eddy currents are spatially inhomogeneous. So for example, in the RONI, we might have a pattern like this, where the odd and even lines are again shifted, but not so much. And here the delay is slightly less. Now in Casebase, all the signal from every voxel is represented in the Casebase center, right? Meaning that now in in Casebase, those ROIs and RONIs are kind of combined, and we end up with a maybe case-based pattern like this. And obviously it's not so straightforward to correct for delays now, because we have like multiple different delays of signals that are like superimposed on top of each other, and we don't know which signal comes from where. So there are a lot of different algorithms that try to account for these kind of higher order phase corrections in EPI. And my personally favorite algorithm is the so-called local algorithm, which refers to this 68 parameters here. You can choose other numbers here. I think the 7, which is not listed here, is also sometimes very popular for like SMS. The 68 refers to local, which means that we actually have 2 parameters that we adjust in aligning odd and even case-based lines. A global one, just shifting respective case-based lines, and also a linear term, meaning that different points in case-base can be adjusted differently in a linear fashion. And also in the fitting algorithm, to find the best 2 parameters, it uses like weights of the signal itself. So if you have a larger signal, then it gets higher weights in finding these 2 parameters. You can also use a global one, which I believe is just 1 parameter of aligning odd and even case-based lines. You can do pixel by pixel or doing none. So I like the local one because it gives me the least ghosts. However, it also means that there is a kind of a non-global phase correction happening, meaning that as soon as you use this phase correction algorithm, even though the ghosts might be less, you cannot really trust the phase of your EPI data, because this algorithm happens on the individual coil level for every individual time point, for most of the EPI sequences, however. And this also means then that you cannot really compare the phase of 2 consecutive time points or 2 different coil elements. And here I want to show you a few examples of reconstructing the same data set with these different phase correction methods from our participant RT. And you can see that the 68 for me kind of looks the cleanest. And the global one down here is also kind of okay, but you have increased ghosts, because here I acquired a data set being very, very close to these acoustic resonances. And the global phase correction scheme cannot really fully account for that, because we have a lot of ramp samplings, and there a certain delay in Casebase refers to a different phase offset that it needs to be correct for. If you do not do any phase correction, it looks worse. Or this is actually the pixel by pixel, which I think looks completely unusable. Another parameter that I find useful sometimes to play around with it retrospectively is the parameter of the so-called reconstruction mode. And this is a parameter that we talked about earlier already, that some sequences allow you to change even in the protocol editor, namely the parameter that determines how the data are saved. If they are saved as magnitude images, as phase images, as magnitude and phase, or also other combinations. So here, for example, if you choose the parameter 16, the default, by the way, is I think 1. If you change this 1 to 16, then you will get not only the magnitude, but you will get the real part of the signal and the phase. And here I show you some examples of this. So this would be the magnitude, this would be the phase, and this would be the real part. So if you want to look at those data and reconstruct the same time series retrospectively in a different way to look at additional data, like in the complex value domain, then this might be a usable and useful tool. Another thing that I found useful sometimes to play around with retrospectively is the parameter that's called UC uncomp images. And this parameter determines if the multi-coil data are saved as combined images or as individual time series, where every individual coil gives you an individual time course. And I do this usually retrospectively, because for like these large coil arrays, this means that there are a lot of data. So if you have a 32-channel Nova coil like I'm using right now, then you have 32 additional time series, which means that the space on the hard drive and the time it takes to export the data from the scanner is multiplied by a factor of 33. So it can take several hours, and the people after you might complain, or the data transfer infrastructure might come to limits. So if you want to change this from 1, where the 1 means that it's uncombined and 0 means it's combined, then in the patient browser you will see a lot of individual data sets, and you see that this is the same time series, it's just weighted from and seen from a different RF channel, which is clearly visible here. For example, that this RF channel is more close to the front of the brain, this RF channel would be more towards the back of the brain. And with this, I want to close by saying that most of the things that I went through today are actually things that I learned from previous mentors and other teachers. For example, I want to thank Robin Heidemann, who is now working with Siemens. And in the early days, he taught me how to change and manipulate the grappa reconstruction pipeline, namely using the improved grappa or also changing the grappa kernel size. I want to thank Markus Streicher for his tips regarding the different Nyquist corrections, the phase corrections in EPI. I want to thank Peter Koopmans for discussions with respect to different partial Fourier reconstruction algorithms, especially with respect to POCs. And I thank Carvin Setson-Pop for helpful comments with respect to the number of iterations that one needs for POCs iterations. I thank Jonathan Polymeni for this very beneficial parameter of the grappa regularization strength. So changing this really changed my life a lot and really improved the TSNR. I want to thank Andreas Schäfer for discussions about complex value MRI signals and how to export that, specifically in combination with individual coil combined images. And I also want to thank my advisor, Benedikt Poser, for everything else. And thank you for your attention.